Today's video is on enthalpy and entropy, two very important terms in thermochemistry. We'll start off talking about heat of reactions. So this is the heat that is either released or absorbed when a reaction occurs between two chemical substances. And we'll start off talking about enthalpy. So enthalpy is represented by a capital H, and it is a measure of the heat content in a chemical reaction. Now we're going to talk about two E words here, enthalpy and entropy. Enthalpy is the one that has an H in the name, and that kind of can help you remember that this is, its symbol is H, and it stands for that heat in the heat content. Now, the heat content of a particular substance is kind of hard to measure. So most of the time what we end up doing is measuring the change in the heat content. So you can see our delta here, meaning change in, and then our capital H, so change in enthalpy. So this is the amount of heat lost or gained when we have a reaction, and it's going to be measured in kilojoules per mole. Now, we've been using Q to measure heat, and Q and delta H are related. I'll get to that in here in just a minute. So if a reaction releases heat, it's going to feel hot, and that's important to remember. You may want to make a note of that. And we call those types of reactions exothermic reactions. I've brought around in class several examples of exothermic reactions, and when you touch the outside of the reaction vessel, it is going to feel warm, or it feels like it's getting hotter. The temperature goes up, and that heat is leaving the system. And so we assign that a negative delta H. I say that the negative means it's leaving, it's getting out of here, the heat is leaving the system, and again, they feel hot. Now, if a reaction absorbs heat, then what we have is an endothermic reaction. I say that the heat's going endos. And the reaction's actually going to get colder. So the heat is absorbed not to make the temperature go up, which is a common misconception, but heat is absorbed so that bonds can be broken, so that energy is being used for something other than temperature. So endothermic reactions feel cold to the touch. An endothermic reaction happens in like a cold pack in a first aid kit. And usually you have that kind of packet, and you're going to feel around, maybe break a vial or just shake it so that you mix the two chemicals inside together, and then it starts to feel colder. Excuse me. Those are endothermic reactions, and we assign them a value of a positive delta H. And again, they feel cold. Now here's where Q and delta H come together. Q equals delta H at constant pressure. Now, that is a pretty common occurrence because we, again, live our lives at pretty constant pressure. And so we will use Q and delta H kind of at the same time. It's just usually different units. Q is usually measured in joules or kilojoules. And so it is for a reaction right now. Delta H is a more universal way to express that change in heat content, and it's kilojoules per mole of what's reacting. And so we can use that and apply that value to other reactions to predict how much heat they are going to produce. Now, sometimes delta H will be included with the reaction. And in order to interpret whether a reaction is endothermic or exothermic, you need to determine if heat is released or absorbed. So here's my first example, and we have heat right here. Now, sometimes it's a number with kilojoules or joules, and sometimes it just says the word heat. So to think about whether a heat is released or absorbed, we need to revisit what the meaning of the arrow is. That arrow means produces, yields, forms. So what we can look at here is that carbon monoxide and this iron 3 oxide react to produce iron, carbon dioxide, and some heat. So heat is being produced here. And so this particular reaction is going to be exothermic. That heat is released. And when we write the delta H value, we have to put this little negative sign here because it is exothermic. That lets other people know that heat is going to be produced by this reaction. Now, if we look at the next example, we have heat right here. Oops, there we are. Heat right here, and it is a reactant. Again, it could be a number or it could just be the word heat. And in this one, what we see is calcium carbonate. You have to add heat to it in order to produce our products. So in this particular case, heat is being absorbed. So our reaction is endothermic. And when we record the delta H value, it is going to be a positive value because this is an endothermic reaction. And this reaction would feel colder as the reaction went on. Okay, so we're going to talk about the driving force of reactions. What makes a reaction proceed to make products or not? So we'll talk about this concept of a spontaneous reaction or a thermodynamically favorable reaction. And this is a reaction that just happens on its own. Now, it makes no mention of how fast a reaction happens. It can take 2 seconds or it can take 2 million years. As long as a reaction proceeds on its own and doesn't have to be forced, then that is a spontaneous reaction. In our experiments, we found that most reactions that are spontaneous or thermodynamically favorable are exothermic. And that kind of makes sense because in exothermic reactions, lots of heat is given off. And so lots of energy is being given off. And so the products are more stable. And things like to become more stable. So most reactions that occur in this world that are spontaneous are exothermic reactions having that negative delta H. But we found that there are some reactions that are endothermic, but they also happen spontaneously. So there had to be another force here that was driving reactions to produce those products. And so we found that the other force is the randomness of the particles in the system. So that kind of desire to be more disordered. And that is called entropy. So that's our second E word. So ice melting is a natural endothermic reaction. At 0 degrees C, ice is going to melt on its own and doesn't have to be forced. And it does that by going from a solid state where there's a whole lot of order, because remember that kinetic molecular theory, particles are just going to be vibrating in a solid. And then when they go to a liquid, those particles can move around a bit more. So there's a bit more disorder in liquid water than there would be in solid water or ice. So entropy, which is represented by the letter S, and I know there's not an S anywhere in that word, but entropy is represented by the letter S, and it is a measure of the degree of randomness, or I like to kind of call it disorder. And if you overemphasize the S in disorder, it can kind of help you remember what the symbol for entropy is. All right. Now, it has units similar to enthalpy of kilojoules per mole, but we have a K here on the bottom, and that stands for Kelvin. So temperature is a factor into how much disorder. Now, that should also make sense according to the kinetic molecular theory, because as temperature goes up, particles move faster, and so they're more likely to be more disordered when they're moving faster. So temperature does play a role. Now, we have really two rules with entropy. And anytime you see the word entropy, you can replace it with the word disorder. So entropy increases, or our disorder increases, as we go from less moles to more moles of gas. Now, this means that if you think about it, if I only have two particles, there's only so many ways I can mix those two things up. But if I have 3 or 4 particles, I can mix up 4 things more than I can mix up 2 things. So if I go to more moles of specifically gas, it is an increase in that disorder. All right, so entropy increases. Another way we can talk about entropy increasing would be going from one state of matter to another. So solids have all kinds of order. All those particles can do are vibrate. Liquids have more disorder. They can move over and around one another. And gases have way, way, way more disorder than solids or liquids because those particles are free and can move independently of one another. So let's see what that looks like in some practice problems. So the entropy of a pure crystalline solid is going to be 0. So that would be our perfect order. And increased heat does increase that molecular motion. If we have a decrease in entropy, it is a negative delta S. That means we're moving towards more order, or our disorder is decreasing. So negative delta S means we're going to more order, and positive delta S means we're moving towards more disorder. So positive delta S, more disorder. Our disorder, and you can read delta S as disorder as well, is increasing. All right, more signs to remember. Okay, so we're going to try and predict the sign of delta S for this reaction. So in this particular case, one of the things that we want to notice is our states of matter. So I have a solid going to a solid and a gas. Well, what's happening here is we are headed towards more disorder. Solids have a whole lot of order. And here we're going to a solid and then a gas. Gases are way more disordered than solids. So in this particular one, delta S is going to be positive because our disorder is increasing. And we're going from a solid to a solid and a gas. Gases are more disordered than solids. Now, here we have another practice problem. We want to predict the sign of delta S for this reaction. So if we look at the states of matter, they're all gases. So this is where we have to use that other rule, and this is going to be the moles of gas. So we're going to get the moles of gas, or at least relative moles of gas, from our coefficients. So on this particular side, on my reactant side, I have 2 moles of sulfur dioxide and only 1 mole of oxygen gas. So that's 3 moles total on my reactant side. On my product side, I have 2 moles of sulfur trioxide. So I'm going from 3 moles of gas on the reactant to 2 moles of gas on the product side. So I'm headed towards more or less moles of gas. So that means I'm headed towards more order. And so delta S in this case is going to be negative because we're going from 3 moles of gas to 2 moles of gas. All right, so let's try a few more. And so if we look at A here, see if you can make your prediction. All right, so this was very similar to our practice problem. And so we have a solid going to a solid and a gas. So we're going to say that delta S is positive. Our disorder or entropy is increasing. We're headed towards more disorder. All right, if we look at B, see if you can predict the sign here. All right, again, we can look at the states of matter here. We're going from a liquid to a solid. So we are headed towards particles that are moving around less. So we're actually headed to more order here. And if we're headed to more order, our entropy is decreasing and delta S is going to be negative. All right, if we look at C, see if you can predict the sign. Here, they're all gases, so we need to go with moles of gas. On our reactant side, we have 4 moles of gas, 1 plus 3. We're just looking at the coefficients. And on the product side, we only have 2 moles of gas. So we're headed towards less moles of gas, so our entropy is going to decrease and delta S is negative. We're headed towards more order. Now, if we look at D, these are those dissociation or ionization reactions we wrote in the last unit. So we have a solid, and we're mixing it with water. And so it's producing sodium ions and chloride ions. So these ions, as a solid, are all locked into place in that crystal lattice structure. Sodium and chlorine ions are floating around in water and can move around more in aqueous solution. So in this particular case, we're headed towards more disorder. And so we have a positive delta S. All right, in E, see if you can predict the sign for that one. All right, we're going from a solid to a liquid, and liquids can move around. Those particles in a liquid can move around more than in a solid. And so in this particular case, we have a positive delta S. We're headed towards more disorder. Our entropy is increasing. And then in F, see if you can figure out the sign of delta S for this one. All right, we're going from a solid to a gas. And so gases are way more disordered than solids. And so delta S is positive for this one. Our entropy is increasing. And this is called sublimation, going from a solid directly to a gas. This is dry ice subliming and the reaction for that.